Okay, so we may start. Now 45 only joined. Okay, so I am properly audible.
Yes, sir.
Yes, sir.
You know that you are aware that recording option is not available now. I am not sure when it will be available.
Sir, what is the syllabus for the midterm?
Okay, I will discuss. As decided yesterday that your syllabus for the for my part, I have I am teaching on function of single variables and several variables. Also, I will discuss multiple integrals, and out of which only the function of several single variables will be considered, and its syllabus up to curvature. And
Sir, can you please repeat, sir?
syllabus for the function of single variable is up to curvature.
Sir, can you please post the syllabus in the classroom?
Do you have any copy or not with you
Yes,
for the
sir.
Yes,
syllabus?
sir. I have the whole syllabus with me. Six
Okay,
serial
so
number.
go to the what is called the function of single variable and up to
Yes, sir.
curvature. You will see that there is only asymptotes is excluded from for the mid semester because some teachers yet to complete this asymptote properly. So it is up to curvature.
Okay, sir.
Okay.
Hmm.
So including everything except asymptote for the function of single variable, except asymptote. This is one. And another thing is probably one teacher is taking on uh, on what is called the improper integral.
Yes, sir.
Sorry, not improper integral, series, infinite series.
Infinite
Yes,
is
sir.
complete, sir.
Infinite series complete, but
Yes, sir.
from other branch it is not completed. So it excluded the power series. Infinite series whole except the power series. Power
Okay,
series
sir.
is the last part. Okay, and
Sir,
then
radius of convergence. Sir, radius of
radius of
convergence.
power series means so radius of convergence everything that included on that.
Okay, sir.
And in differential equation up to the method of variation of parameters. Found it in the syllabus, method of variation of parameter up to. Got it or not? Hello?
Yes, sir.
Got it in the syllabus?
Yes,
And
sir.
sir,
Yes,
and sir, improper
Okay, so
integral.
improper integral started or not? I think improper integral not started.
No, sir. It started, sir. Beta gamma function, mu test.
Started, but it is
Not completed, sir. Continuing.
not completed. So the syllabus is uh, for the function of single variable up to curvature, that is everything including curvature, sorry, excluding asymptote. Everything for the function of single variable except curvature. Sorry, asymptote. And for infinite series, it is whole infinite series except the power series. And for differential equation, up to uh, up to method of variation of parameters, up to method of variation of parameters.
That means, sir,
Okay,
here
this is
higher
your
order. Sir, higher order
Hmm?
ordinary differential equation with constant coefficient, Euler's equation, and
Everything up
method of
up to
this.
method of variation. Everything in your syllabus up to the method of variation of parameter. Okay,
Oh, okay, sir. Okay, sir. Thank you.
including method of variation of parameter. Including method of variation of parameter. Everything as written in your syllabus from the beginning, including method of variation of parameters, up to and including method of variation of parameters. Okay, and you know that there will be 7 questions. You have to attempt 5, and first 5 evaluated answer. First 5 answer. Sorry, first 5 answer will be evaluated. If you make 6 answer, only first 5 will be answered. So 6 into 5, that is 30 marks. Okay. Okay. So let us start Taylor's theorem for the function of Taylor's theorem for the function of two variables. We are continuing on the function of several variables, but mostly we are discussing function of two variables. We may consider function of three variables, but it is limited to some cases for partial derivatives here and there, everything for something. Here, the Taylor's theorem we have discussed for the function of single variables. Here it is the function for the function of two variables. Look at this. Here the function. Here the function is just a minute. Okay, so here the Taylor's theorem. Here fxy is a function of two variables, and possesses continuous partial derivative, because here the function of two variables of order n in any domain of a point AB, and the domain is large enough to contain a point A plus H, B plus K. So if you consider a domain here, suppose for example this is a point, so you will consider a domain of this. Say for example, here is the point A plus H, B plus K. That point must be in the domain of the point AB. That is, there is a neighborhood of the point AB which contains the point A plus H, B plus K. In that case, there exists a positive number theta. Already you are aware about the number theta, which is always lies between 0 and 1, such that the expansion of the function at the point A plus H, B plus, just a moment. Just a moment. Okay. So at expansion of the function at the point A plus H, B plus K is FAB, and this is the due to the partial derivative H del del x plus K del y FAB. That is H del x of FAB plus K del y of FAB. That is del y of F at the point AB. Remember this. Similarly, the third term 1 by 2 factorial is del x plus K del y whole square FAB, And you know that h del del x plus k del del y whole square means actually it is h square del square f by del x square plus 2 h k del square f by del x del y plus k square del square f by del y square, where at the point AB. All these are at the point AB. Similarly, if you will get the fourth term, whole cube, and so on. And the last term is known as last term is here. Look at this. Last term is the remainder after n terms, and this remainder is 1 by n factorial h del del x plus k del del y whole to the power n f a plus theta h b plus theta k. Suppose you have to find a remainder after 3 terms, then what will be the Rn? Then R3, 1 by 3 factorial h del del x plus k del del y whole to the power 3 f of a plus theta h b plus theta k. So this is the Taylor's theorem for the function of two variables. It is almost the same thing that we have done for the function of single variables, except here since it is two variables, we are taking the partial derivatives. And one thing, we will not prove this theorem here. It is not included in your syllabus. So just remember the statement. It is very important. And you know that when we consider Taylor's theorem, we also consider different of its form. And whenever we will use for any function, depending on the question, we will use the different form. For example, if you put a equal to 0, b equal to 0, that is, it is near 0, 0. Here it is 0, 0. Then if you take any point here, that is actually hk, not a plus h, b plus k. And if you would like to expand the function in terms of x and y, then we take h equal to x and k equal to y. And in that case, fxy equal to f0, 0, same thing you have found here in the Taylor's theorem. This is the same thing, just replace a and b as 0, 0. So you will get 0, 0, 0, 0, and so on. And h and k will be replaced by x, y. If the expansion is in powers of h and k, then you can write h and k. If the expansion of the function in powers of x and y, you have to write the function in powers of x and y. And in that case, the remainder after n term, then look at this, Rn equal to 1 by n factorial x del del x, y del del y whole to the power n. Same thing as it is in the, for the Taylor's theorem, except here the point a and b are 0. So a and b are 0, that is only theta x, only theta y. And you must mention that 0 less than theta less than 1. So whenever you would like to expand the function in powers of x and y only, then you will use this theorem. This is, you already aware that this theorem actually, this form of the Taylor's theorem actually known as the Maclaurin's theorem. Similarly, if we would like to if you would like to, just a moment, adjust. Okay. Similarly, if you would like to expand the function in factor of x minus a, y minus b, or any other form, then accordingly you have to replace the theorem in that form. For example, look at this. Here, if in any question a function is given and the question is expand the function in powers of x minus 2, y minus 4, then you may use this form of the theorem. It is the same thing. Same form. If you remember the form 1, you will get every form. And in that case, your function was f of a plus h b plus k. So here left hand side xy. So if you take a plus h equal to x and b plus k equal to y, then left hand side will be x plus y. And h will be replaced by x minus a. So look at this. So just it is different, written in different form, but it is not deviated from the Taylor's theorem. All these are different forms of the Taylor's theorem. Okay. So here in case of the function of two variables, we have studied three forms. One is the Taylor's theorem, normal form, f at the point a plus h b plus k. Then is a special case at the near the origin, that is a is taken 0, b is taken 0, that is known as the Maclaurin's form. And this is another form when the function to be expanded in powers of certain factors x minus a, y minus b type. And here it is one example is given, the function e to the power xy. Here e to the power xy at 1 1. Expand x e to the power xy at 1 1. At 1 1 means it is a factor like x minus 1, y minus 1. So the function to be expanded in powers of x minus 1, y minus 1. So first remember the form of the Taylor's theorem. When you are expanding the function in powers of x minus a, y minus b. And here look at this, you have to evaluate the function at the point a, b, partial derivatives at the point a, b. So here it is, look at this, fxy equal to xy at 1 1, it is e. fxxy, that is partial derivative with respect to x, that is this, and that is also e. All are e. 2e, here it is 2e, 2e. It's just differentiate and substitute 1 1. Then think about this form and substitute there, you will get this. Now you may ask me that how many terms you will write. If nothing is mentioned, then you can write first 2, 3. Here it is used 3 terms. First 3 terms, that is enough. If it is given that up to powers of 3 up to powers of 4, then you have to take up to those number of terms. Remember that. But if nothing is mentioned, then this is enough. This is enough. The expansion of the function e to the power xy in powers of x minus 1 and y minus 1. Have any question?
No, sir.
Sometimes you will respond, otherwise sometimes it is happened that my network disconnected. I am continuing, and in the last class after 5 minutes they called me that I am disconnected from this classroom. Is it okay?
Yeah.
Yes, sir.
Okay. Okay, so this is one example. I will show you different types of example. Okay, here look at this. Expand e to the power x sin y in powers of x and y as far as terms of third degree. Look at this. Here e to the power x sin y is the function, and here not in powers of x minus a, y minus b. Here in powers of x and y only, means about 0 0. Also it is given as far as terms of third degree. That is, you can keep terms up to 4th degree, no problem, but not 2nd degree. 3rd degree minimum minimum third degree term you have to consider. Okay, so in this case, use the Maclaurin's theorem. This is the Maclaurin's theorem. Fxy equal to f00 x del del x y del del y at the point 0, 0, and then the second derivative, and so on. And for this purpose, look at this. You have to evaluate the function at 0, 0. You have to evaluate the first partial derivative with respect to x and y at the point 0, 0. You have to evaluate the second partial derivative with respect to x, with respect to y, and mixed with respect to x and y at the point 0, 0. And since here it is as far as terms of third degree, you have to consider this one also. Otherwise, you will not get the terms up to third degree. So here it is x del del x, y del del y. That is third order partial derivative at the point 0, 0. Third order partial derivative with respect to y at the point 0, 0. And some other mixed term also you will get. Mixed order partial derivatives you will also get. And substituting all these evaluated partial derivative, these are all evaluated. Substitute in the Maclaurin's theorem, you will get this one. So this series, this expansion of the function contains as far as terms of the third degree. If you are more interested for another term, you can take, but it will take much more time, because to the power 4 means you have to you have to consider some partial derivatives at the point 0, 0, then you have to substitute here. So earlier example was about x minus 1, sorry, inverse of x minus 1, y minus 1. This example, inverse of x and y. Okay. This is another example. Just a moment. Okay, this is this is another example. Polynomial function x square y plus 3y minus 2. Sorry. This is the function, and look at this here, in powers of x minus 1 and y plus 2. So what will be the point? If if your expansion in powers of x minus a, y minus b, then it is about the point AB. So here it is in powers of x minus 1, y plus 2. So it is about the point 1 minus 2. And here also, look at this. Look at this. Here it is a third degree polynomial equation function x square y. So third degree polynomial. So if you take fourth degree, fourth order partial derivative, then obviously it will be a 0. So remember this. Only you have to do up to third order derivative, partial derivative. And since here it is x minus 1, y plus 2, you have to use the third form that I have discussed. So functional value at the point 1, 2, minus 10. Partial derivative at the point 1, minus 2, minus 4. Partial derivative with respect to y, minus 4. fxx, minus 4. fxy, 2. fyy, 0. And fxx 0, fyy 0. These are also 0. And fyxx 1 minus 2 equal to 2. Because here it is mixed x square and y. X power of x is 2 and y is 1. So up to second partial derivative and first partial derivative of y, it is one constant. And all higher order terms are 0. If you take more derivative of this function, obviously it will be 0. Now substitute to the third form of the Taylor's theorem that I have discussed. You will get this. And also remember that don't simplify this expansion, because the question is in powers of x minus 1 y plus 2. Sometimes you simplify it and write in powers of x and y, but question is not that. Remember this. Okay, next another example. Expand e to the power x cos y near the point 1 pi by 4 by Taylor's theorem. 1 pi by 4. You will solve it. It's same thing that we have already solved here. E to the power x sin y here in powers of x and y, and here expand e to the power x cos y in powers of x. Here it is given near 1 pi by 4, that is in powers of x minus 1 y minus pi by 4. That is, you have to find the value of this function at 1 pi by 4 and its partial derivative at 1 pi by 4, then substitute to the third form of the Taylor's theorem. You will get the expansion of the function. At least take 3 terms, first 3 terms, that is enough. You don't have to do much more. Okay. So these are some examples for the expansion of the function using Taylor's theorem for the function of 2 variables. It may be about 0, 0, it may be about some other points. It may be mixed like that, say for example, it may be like that, it is about say 2, 0. Maybe it is one origin or the other point. So in that case, one y will be in powers of y. Expansion of the function is in powers of y and x minus 2. So remember this. Okay, then I will give one different types example. First, look at this portion. Try to understand this one. This is one note that an important application of Taylor's theorem consists in estimating the effects of small changes in the variables. Small changes. Earlier, I have not mentioned whether h and k are small or not. Here, it is a particular case that Taylor's theorem consists in estimating the effect of small changes in the variables. Small changes in the variables means if this is the point, another point is taken very close to this point. If this is the point and another point is taken very close to this point, in that case the h, this is h, and this height, this is k, are very, very small. If h and k are very, very small, we can neglect the higher order terms. That is, if h is say 0.001, if you take its square, it will be very, very small. Similarly, k, yes, square will be very, very small. If you multiply h and k, that will also be very, very small. So, if x plus h, y plus k, that is, you are expanding the function about xy and its increment is given hk, which is very, very small, then its expansion is this, this, and this. Plus, there are n number of terms and we will remain that. But since h and k are very, very small, if you look at this portion gives very small contribution. So we may neglect it. You know that we sometimes neglect very small quantity. So its approximate value is this. It is not use actual value, because whether it is small or not, that is, but it will contribute something, but we are neglecting that one. So it is approximate value. That is, we are taking only the linear term. Fxy plus h del del x plus k del del y into fxy. It is possible. We consider this case only when there is a small changes in the variables, very small changes in the variables, and this result can be used to find an approximate value of f a plus h b plus k. That is, you know the value at the point a b, and you need to find the value very near to that point. In that case, this theorem can be used up to this, considering only the linear terms. Now look at this. Here, look at this. Find an approximate value of root over of 5.01 whole square plus 12.02 whole square. And by observation, and after this, after solving this example, you will understand what you have to consider the variable and what its increment. Here 5.01, 5 is the variable, and here 12.02, 12 is y, here is taken, and its increment is very, very small, h equal to 0.01 and k equal to 0.02. Now what you have to do? The question is find the approximate value of this function. So when we are finding the approximate value, when h and k are very, very small, we can neglect the higher order terms. So our approximate value will be this one. That is fxy, that is f at the point 5, 12. And then h means 0.01, k means 0.02 at the point fxy at the point 5, 12. So take the first derivative with respect to x, with respect to y, and you have to use this one. So fxy, that is root over of 5 square plus 12 square, and h 0.01 del del x of fxy, that is x by root over of x square plus y square, that is equal to 5 by root over of 5 square plus 12 square. Similarly, k del del y of fxy, k means 0.02, and del del y of fxy means y by root over of x square plus y square, that is 12 by this one. So after simplification, here is some portion is gone. So you will find the result, you will get some value, which is the approximate value of this one. So this is one application of Taylor's theorem to find the approximate value of the function when the variables are changes very, very small. Hello, I am in the
Yes, sir.
have any question?
No, sir.
No, sir.
Okay. So if you have any question, you must ask me.
Sir,
Yes.
Sir, is radius of convergence in syllabus?
Radius of convergence is not in your syllabus. It is under power series. So radius of convergence is not in your syllabus.
Okay, sir. Thank you.
Just a moment. Okay. So next, another thing. Okay. Taylor's theorem gives us the approximation of fxy to a polynomial in xy. Linear approximation is this. Linear approximation. Linear approximation is this. Then what will be the error? Because you are when you are neglecting certain terms, then you are not getting actual value. You are getting some approximate value. So there must have some error. So what will be the error? Look at this. This is the error. Actually, this is the next term. Here I have considered fx not this is the second term. Next third term is what? Whole square x del x plus y del y whole square f of this, and that is considered as the remainder after two terms because we are neglecting all other terms. So that's why look at this. Here it is written theta into this, theta into this, theta into this, and here also theta, because this is considered as the remainder after two terms. So if you need to find the error, error, then you have to find this value. And when you are getting approximate value means you are considering only linear terms. So rest of the terms are error. You are not considering. And in that case, you know that we are taking remainder after n terms as Rn. So here, since we are considering only the first two terms, rest all the terms are remainder. And that remainder after two terms. So it is term is this. This is the term second after second term, and here this a plus theta h, that is theta into this. Theta lies between 0 and 1, and this is the error. Okay, next take one more value. Compute the approximate value of 1.04 to the power 3.01. So function is like x to the power y, x equal to 1, y equal to 3, and changes of the variable h equal to 0.04, 0.01. So these are considered very small changes of the variable. And so we will consider only the linear term, that is fx, fy, not fxx, not fyy, and its value add x to the power y x equal to 1, y equal to 4, so it is 1, and here also it is 3, because 3 into 1, here also it is log 1, so log 1 means 0. So substitute here, you will get the value, that is 1.2 approximate value. So this is all about Taylor's theorem for the function of two variables. Later we will discuss some more examples of different types, but after finishing the syllabus. And also I will take one class test for your internal assessment, teacher's assessment, and it is about it is 20 marks. So uh, because you are just uh, near to your midterm exam, so I am thinking I will consider it after midterm. Is it okay, or in the next week? If you are agreed, then you may in the give in the
No,
next
sir.
week
After
also.
midterm, sir.
After midterm, sir.
After midterm, like
Okay. So, but remember that you have to give one exam, class test.
Yes, sir. And sir, before the class test, sir, 7 days. Please tell us the syllabus of the class test.
Okay, okay. Don't worry about this syllabus. As you like, if you think that we will give only on those topics, you may give it, no problem. But you will inform me that we will give on these. Okay, next I will start the maxima minima. It is for the function of two variables. Maybe for the function of three variables also, but with certain constraint. So we can eliminate one variable, so it will become two variables. So take 10 minutes rest, because I am not in hurry, because it is in near to your midterm exam, and after maxima minima, I have to also discuss about the multiple integrals. Mostly we will consider two-dimensional integral area. Some examples also will be given on volume integral, how to evaluate multiple integral. Okay, take 10 minutes. After 10 minutes, we will little start about the maximum minimum. Very simple, because no proof is there, only the methodology and some examples I will show you how to solve, how to find the maximum minima, and what is the concept of maxima minima in case of the function of two variables. Okay, so we will start again at 10 minutes, after 10 minutes later. Okay. Are you ready?
Yes, sir.
Yes, sir.
Okay. So let us start another topic. It is also in the field of the function of several variables, and here it is the maxima and minima. Maxima and minima. So how you will determine the maxima minima of a function? Up here it is considering two variables. The first, the what is the concept? First, you know that in case of single variable also, you when do you have idea of the maximum minima for the function of single variable?
Yes, sir.
Okay, so that's why it is not included in the syllabus here. And here you know that when you are getting maxima minima for function of single variable, say for example here in this direction x, and here it is fx in this direction. So suppose function is like that. So function has a minimum at this point, minimum at this point, minimum at this point, etc. And maximum at this point, also maximum at this point. You cannot say that this is not maximum because it is maximum, because actually we are considering maxima and minima means we are considering the maxima minima, local maxima minima. Local maxima minima means what? It is minimum within a neighborhood of this point. Suppose here it is minimum, it is neighborhood. We will compare this value of the function with its neighboring value. We are considering this value with its neighboring value. We are not considering this value with this value. So here all are doing is considered local, that is within a neighborhood of a given point. So here also in case of the function of two variables, we will consider the function maxima minima in a neighborhood of a given point. Suppose that a function fxy is said to have a maximum where, first considering maximum then minimum, maximum value at a point AB of the domain of fxy, provided we can find a positive quantity delta such that for all values of xy in this and this, x not equal to a, y not equal to b, fab greater than fxy. So suppose this domain of the function is, say for example, this is the domain of the function, and AB any point, here it is AB any point, this point is AB, and we considering a neighborhood this. Suppose this is the point, this is AB. So if A plus delta means up to this, A minus delta up to this, B plus delta up to this, B minus delta up to this. So this point is AB. So in this region, in this neighborhood, at all other points means if you consider the point here, if you consider point here, here, all other points at which the function to be evaluated, and if it is evaluated at the point AB, then this point, at this point AB, FAB greater than FXY. If this is happened, then we say that fxy has a maximum value at the point AB. But if the others reverse thing is happened, that is if AB less than of fxy for all other points, if you are evaluating function
Hello, sir, you are not audible. Hello.
Probably I was disconnected.
Yes, sir.
Sir, you are disconnected.
Hello, I am audible.
Told you.
Now
Yes, sir.
audible.
Yes, sir.
Now audible, no? Okay, okay, no problem.
Yes,
So
sir,
that's
audible.
why I told you that sometimes it is happening nowadays. Okay. So first to find the maxima minima. What you have to do? First partial derivative will set 0. Find the points. At that point, check whether this expression fxx fyy minus fxb whole square, this fxx fyy minus fxy whole square greater than 0 or not. If this is greater than 0, then maxima minima exist, and that is maxima or minima, that will depend on the sign of fxx ab or fyy ab. Negative maxima, greater positive minima. If it is less than 0, then no maxima minima. If it is 0, then you cannot say anything from here. It needs further analysis. I will show you some example also. First, take one example. Here, look at this: fxy equal to y square plus 2x square y plus 2x y4. So that fxy has a minimum at 0, 0. fxy has a minimum at 0, 0. So what you have to check? First, take the first partial derivative with respect to xy, second partial derivative with respect to x with respect to y, mixed partial derivative fxy. Now at the fx 0, 0, 0 or not, at 0, 0, at 0, 0, fx 0, 0, sorry, fx 0, 0, 0, fy 0, 0, also 0. So it satisfies this first partial derivative with respect to x and y. Now check whether fxx fyy minus fxy greater than 0 or not. Here look at this: fxx 0, 0 means here it is 0. Fyy it is 2, and fxy also 0. And the condition is what? Fxx fyy minus fxy whole square greater than 0 or not. So here it is what? Uh, what is the value of fxx fyy minus fxy whole square? It is 0, because 0 into 2 minus 0 square. So it is 0. So we cannot say anything from here. We need further analysis. And that is also very simple for this example. So always it may not be possible. Here look at this: fxy equal to y square plus 2x square y plus 2x to the power 4. That is x square plus y whole square. So at any value it is positive except 0, 0. So 0, x square plus y. So if you take any negative, positive, whatever be the values of x and y, it is always greater than 0 except 0, 0. At 0, 0, what is the value? At 0, 0, f 0, 0 equal to 0. So look at this: fcd less than fxy, then cd function has a minimum value. So f0, 0 less than fxy for all xy. Here it is all xy, but if you take any neighboring points of 0, 0, then also it is 0. Less than this one. So you can say that the function has a minimum value at 0, 0. If you have any question, you may ask me. I told you that three conditions you have to follow. One is fx, fy at the point these are 0 or not. It is 0. Next, move to fxx, fyy minus fxy whole square. Check its sign. It is positive, negative, or 0. Positive, then okay. Then maximum or minimum, and fxx, check the sign of fxx. That will give you the max, show you whether it is maximum or minimum. If fxx or fyy minus fxy whole square less than 0, neither maxima nor minima. It is your conclusion. But if this is 0, then you cannot say anything from here. Further analysis is required, and this analysis that I have shown here, it is showing that function has a minimum value at 0, 0. So here it is f00 less than fxy for any xy near 0, 0. In case here, particularly for this example, for any xy, not near 0, 0. For any xy, f00 less than fxy. So the function has a minimum value at 0, 0. Okay. Next example is find the maxima and minima of the function, this one. No points are given. So you have to find the points if exist. If exist means first take the first derivative with respect to x, first derivative with respect to y, that is fx and fy, and set fx, fy 0, fx 0, fy 0, you will get these two relations. Now solve these 2 points, solve these two equations, and you will get how many points? 4 points are there. You will try to solve the these equations. It is also not so easy. So easy in the sense that it will, if you move in different way, it will take more time. You will be able, finally you can find these points, but it will take more time. So all possible, taking all possible combinations, we are getting 4 points. How? Setting fx equal to 0, fy equal to 0. Fx equal to 0, fy equal to 0. These are giving two equations A and B. Solving these two equations, because these are nonlinear equations, y cube, y square, x cube, all are present here. So it is giving 4 points, 0, 0, 3 by 2 minus 3 by 2. Oh, sorry, 3 points. 0, 0, 3 by 2 minus 3 by 2 minus 3 by 2, 3 by 2. Now at each point you have to check. Now at 0, 0, fxx 8, fyy 8, fxy equal to minus 1. So fxx, fyy minus fxy whole square, that is 64 minus 1, 63, greater than 0. So either maxima or minima exist. Now what you have to do? You have to check the sign of fxx or fyy. If you check fxx means what? 8. So it is greater than 0. That is at 0, 0, the function has minimum value. And if the question is also find the value, then you have to set 0, 0 at this function. You will get the minimum, sorry, at this function. You will get the minimum value. But if the question is not only find the points, then this is enough. Next, at the point 3 by 2 minus 3 by 2, 3 by 2 minus 3 by 2, and here also, sorry. No, here it is negative. So neither maximum nor minimum. And at minus 3 by 2, 3 by 2, minus 3 by 2, 3 by 2, here also this is negative. So the function has neither maximum nor minimum. This type of example is good for your exam because here neither maximum. If any one is greater than 0, then you have to check if fxx, then find the value of the maximum minimum value. It will take little more time. But if it is negative, then in one word you can say that neither maximum nor minimum. Okay, little different types. One more little different type. For example, find the minimum distance between the origin and the plane 2x plus y minus z equal to 5. Find the minimum distance between the origin and the plane. What is the distance? If you take any point pxyz in the plane, then you have to find the distance between 0, 0, 0 and xyz. That is taking any point pxyz in the plane, the distance between the origin and the point xyz is this. So instead we are considering now the function this one. We are considering this function. We are not taking roots because if this function has a minimum value, then root over of this function will also have a minimum value. Now what is the question? Find the minimum distance. So we have to find the minimum value of this function. Again the same thing you have to do, but look at this. Here 3 variables are there, x, y and z, and the point is taken in this plane. So from here you can find z equal to what? Z equal to 2x plus z equal to 2x plus y minus 5. Now substitute here. So you will get this function as a function of 2 variables. Now you can use the same theory that I have discussed. First partial derivative, second first partial derivative with respect to xy, that is this and this. Then del square f del x square, del square f del y square, del square f del x del y, etc. Now solve these two equations. If you solve these two equations, you will get x equal to 5 by 3, y equal to 5 by 6, and since z equal to 2x plus y minus 5, substitute x and y, you will get z equal to minus 5 by 6. So this is the point on the plane. Now check whether this condition is satisfied or not. fxx fyy minus fxy whole square, that is equal to 24, greater than 0. So either maxima or minima exist. And then what you have to check? fxx, this is 10, greater than 0. So the minimum value. And what is the minimum value? Substitute here xyz, 5 by root 6. So this is the minimum distance from the origin to the plane x 2x plus y minus z equal to 5. If you have any question, you may ask me. So here one new thing is that here the function is a function of 3 variables, but there is a constraint. From here we can eliminate one variable. And we now it is a function of two variables. We can use the same theory that we have developed earlier. Okay, this is one example, almost the similar type. Look at this. Find points on the surface z square equal to xy plus 1 nearest to the origin. The same thing earlier that we have root over of x square plus y square plus z square at other point is 0, 0, 0, fx, y, z, this, but it is a function of two variables, but we can remove z from here, so it is a function of two variables, say fxy equal to this. Now you have to solve it using the same techniques that I have discussed. And here it is one simple example. Just a polynomial function is given, so fx, fy, this is check. Now read this problem, then I will discuss. So that the function fxy equal to mod x plus mod y attains its minimum value at 0, 0, even if fx 0, 0 and fy 0, 0 does not exist. Fx 0, 0, fy 0, 0 does not exist, but the function attains its minimum value at 0, 0. What is the conditions for the maximum minimum? That if fx 0, 0, fy 0, 0 exist, then these are 0. But here does not exist. So you have to check both that fx 0, 0 does not exist, fy 0, 0 does not exist, and the function attains minimum value at 0, 0. First check whether fx 0, 0 exists or not, fy 0, 0 exists or not. So fxy equal to this and f0, 0 equal to 0. Why? If you set here 0, x0, y0, then this is 0. Now fx 0, 0 equal to what? Definition, limit h tends to 0. I told you here it is derivative with respect to x only. So y is constant. Variation is given only on x. So it is 0 plus h, 0, f0, 0 by h. f0, 0, 0 and f h0 equal to what? y0 mod h. So mod h by h. And you know that if h tends to 0 plus, then it is 1. H tends to 0 minus, then it is 1. So it is written here 1 minus 1 according as h tends to 0 plus or 0 minus. So fx 0, 0 does not exist. Similarly, fy 0, 0 does not exist. You can check it easily. Now you have to show that the function attains its minimum value. Now check fxx 0, 0, fxy minus f0, 0 equal to this. This is greater than 0. Whatever may be the value of x and y, except both are 0, then it is always positive. So fxy greater than f0, 0. That is f0, 0 less than fxy. That is f at 0, 0 has a minimum value. Any question? Okay, this is another example. Find the point on the plane x plus by plus cz equal to p. Do you know this type of plane, three-dimensional plane? Have idea?
Yes, sir.
Okay. Three-dimensional. It is plane, not this two-dimensional plane. It is just like this. So plane X, Y, Z.
P
It
the
is just
perpendicular
like
distance.
this. Yes?
P the perpendicular distance, sir.
Yes, yes. P is the perpendicular distance from the plane from the origin to the plane. P is the perpendicular distance. Yes. Okay. So the question is uh, find the point on the plane x plus by plus cz equal to p at which the function this has a minimum value and find the minimum value. Remember this, whenever you have question is find the minimum value, also you will find minimum value, otherwise your marks will be deducted. And some question it is only the check whether it has minimum and maximum, then in that case you don't have to find the minimum or maximum. Okay, here fxyz equal to this function given, this one, and the constant is this, because you have to find a point on the plane. So xyz, if the point is xyz, then it will satisfy this equation x plus by plus cz equal to p. So only what is the advantage of this, that here it is a function of three variables. Now from here z eliminate, z equal to 1 by c into this. So fxyz, that is equal to now function of two variables this. And now use the same technique, fx0, fy0, that will give x and y, and if you substitute in this equation you will get z as this. Next, partial derivative at the point, at these points, that is greater than 0. Then check this one, the here answer is given, but you have to calculate it. Here it is greater than 0, here it is also greater than 0. So at x, y, z given in this has a minimum value, and minimum value, what is the minimum value? Substitute in this equation, sorry, in this function fxyz equal to x square plus y square plus z square, you will get the minimum value. And in the next class we will discuss about the that is also maxima minima, and in your syllabus it is given as that Lagrange's method of undetermined multipliers. I will explain the technique together with some examples. That is another technique to find the maxima minima, the function of two variables, three variables, whatever it may be. Lagrange's multiplier, known as the Lagrange's multiplier. That is in another class, maybe in the next class. Okay, that's all. Practice.
Thank you, sir.
Okay, if you have any question, you may ask me, otherwise we may leave.
Sir, this chapter is not on mid semester.
No.
Minimum, sir.
No function of several variables.
Yes,
Nothing of function of several variables. Only the function of single variables, that also excluding asymptote. Okay.
Okay, sir.
Okay. So I am leaving.